So the subject of my talk is flatbands construction and perturbation, and it summarized the work we did over the past, I would say, 5 years. And I should also point out that there's a companion talk. So after Arul Lakshminarayan presents the dual unitary circuits, Carlo Danieli, who's sitting over there, will continue more or less where I leave. So to begin with, let me present briefly the people involved into this, who participated at various stages of this project. So Sergei Flach is the director of the PCS Center. So Tilen Chadish, who's I believe is somewhere in the audience, Youngjun Kim and Sang-Hun Lee, the two PhD students sitting in the back, as well as Carlo Danieli, Ihor Vakulchik, who has now left the center, and Arindam, Ibrahim, and Nana, who are also part of our team but have now moved elsewhere. So the brief outline, what I'm going to present are what are flatbands and why we think they're interesting. And the main issue I'm going to address is how do we find them systematically in various settings, that is in 1, 2, and 3 dimensions for various geometries, perhaps including things like DC fields, and I'm going to briefly mention Floquet and many-body settings. And the second question is, once we construct the flatbands, what do we do with them? We actually want to perturb them and understand also in a systematic fashion what kind of reaction do they show to various perturbations. And again, I will focus on the case of disorder. So I'm basically staying with the single particle systems, while Carlo will cover the more complex case of nonlinearities and many-body interactions. So let me begin. So the question we're interested in, like the main question we're trying to address, is what happens if you take a highly degenerate state, and also the question is how do you find such a state? What happens if you perturb it? What is the outcome? How can you predict and how can you find interesting cases? So because of the huge degeneracy, any perturbation is relevant, and you might expect something interesting as an outcome. And the flatbands I'm going to talk about are just one example of degeneracies, and an interesting question to which currently not much is known is the genuinely many-body degeneracies in the many-body spectrum. And to give you a few examples of what interesting outcomes you might expect is the Landau levels and the related quantum Hall effect, where you combine the flatbands with the interactions, the flatband ferromagnetism, the systems where one can prove the existence, more or less rigorously prove the existence of the ferromagnetic ground state, the flatband enhanced superconductivity, and the example I like most, just my personal taste, the classical spin liquids, where you can demonstrate that this combination gives you the genuine magnetic monopoles, which, again, to the best of my understanding, have not been observed in nature, well, let's say in the Maxwell setting, but funnily were observed in condensed matter systems. So now the more technical definition. So what is a lattice flatband? Basically, it's a situation when one of your bands in a tight binding model turns flat and has no dispersion. Typically, such bands, definitely for the short range Hamiltonians with translation invariants, feature compact localized states, that is eigenstates with strictly finite support, and this is really an important feature that is the cornerstone of the whole construction I'm going to present. So it's also quite obvious that if you just take a random Hamiltonian and look at its band structure, random translationally invariant Hamiltonian, and look at band structure, none of the bands is going to be flat. So you need quite some fine tuning. And this also tells you that this fine tuning is fragile to perturbations, and that's again why these objects are interesting. Even though they're fragile, you might expect interesting phases to emerge. And also what turns out is that even if you're not exactly at the flatband point, but sufficiently close in proximity, it still affects, say, the ground states or the phenomena that you observe. So as I've already mentioned, it also tends to stabilize some exotic phases or unconventional orders or enhance the already known phases, superconductivity being one example. And here are the few simple examples of tight-binding Hamiltonian or tight-binding lattices exhibiting flatbands, like the diamond chain or the 1D checkerboard, sorry, the 1D Lieb, the stub lattice, dice lattice, well, the 2D Lieb, they all feature flatbands. Now, how do you find them? So the interest in flatbands, like the first example of flatbands, I think were discovered in the late 80s. And since then, people came up with a plethora of methods to identify flatbands in the tight-binding models, like certain symmetries, typically the ones that tell you that for any eigenstate of energy E, you have an eigenstate with energy minus E. You can quite easily construct Hamiltonians with a flatband, and this includes chiral symmetry, also certain local symmetries, latent, or as we have recently discovered, the NTPT as well as PD symmetries. You can also use graph properties like origami rules, where you start from a relatively trivial construction that has a flatband, and you apply a number of unitary transformations that ensure the flatband is there, and you end up with a non-trivial Hamiltonian. Well, the line graph construction, which includes, let's say, the well-known Kagome lattice, can also try stacking mini arrays, which induces a flat band, say, in the case of the diamond chain, due to the presence of the bottleneck sites. Gram matrices Aronov bomb cages, which, say, present in the dice lattice in the magnetic field. Finally, you can try to do the manual fine-tuning and just, by changing the parameters of a given Hamiltonian, try and see if you can turn one of the bands flat. So you can easily see from this list, these are at best some classes, certain classes of Hamiltonians or specific cases, and they are by far not systematic, which is precisely the question that we try to address. Can we explore this manifold of flat bands systematically so that we can understand the generic properties, and as well as understand their reaction to perturbations in a systematic way, and see if we can find something interesting? And so to achieve that, what we eventually discovered is that there is indeed a systematic way to classify flatbands, simply by considering the relevant parameters, which is the space dimension, the number of bands, the hopping range, and eventually the size of the compact localized state. Remember, I told you that's the key concept. As well as perhaps lattice symmetries, if you want to incorporate any into your Hamiltonian. Well, eventually you might also consider whether you want any band touchings your Hamiltonian or not. So once you fix that, it's actually possible to reconstruct, to construct flatband Hamiltonians at will. Basically starting from the CLS, which is the fundamental piece. So again, so how do you do that? Let me start with a slightly different question. Imagine you already have a Hamiltonian with a flat band. So then for a short range, translationally invariant Hamiltonian, you know that it has compact localized states. How do you find one? So, well, the idea is very simple. You just start with the smallest possible block, which is typically just one unit cell, and you try to check whether you can find an eigenstate that fits into a single unit cell. If it doesn't, so if you find no solutions, you just continue by looking at 2 unit cells, 3. In higher dimensions, you might perhaps consider various shapes, and you can try and see what is the shape you need to find the solution. And again, because you have a flat band, you're guaranteed to stop at some point. So the main idea of our classification is basically to inverse this procedure and go in the other direction. So you simply fix the dimension, fix the number of bands. You say how far you want to allow the particles to hop. You fix the size of the CLS, and in higher dimensions, beyond 1, also the shape. You fix the flat band energy. In our construction, that's an input parameter. You can choose its value at will. It turns out that this 5 input data enforce some constraints on the possible compact localized state amplitudes. And once you fix that, the problem, so essentially once you find the CLS amplitudes, you end up with what is known the inverse eigenvalue problem. You know part of the spectrum of your Hamiltonian, the flatband energy and the compact localized state, and you want to see which Hamiltonians are compatible with it, and that is basically a linear problem that's easily solved. So furthermore, this last step, so solving the inverse eigenvalue problem, also in principle allows you to incorporate the lattice geometry. Up to now, I made no constraints on which hoppings are allowed and which are not. But in principle, you can also request that certain hoppings are zero, and this allows to address a problem that if you have a given network, what kind of Hamiltonians would support a flatband on it. And another extension is the ability, again, this construction extends naturally to the non-Hermitian settings, and can be used as the CLS tester. That's what I started with, and these results are more or less, this is summarized, the results of these 4 papers. So let me show you how it works in the very simple example of the 1D ladder with nearest neighbor hopping. So this is the set of the equations for the Hamiltonian that you need to solve. So here, H0 corresponds to hopping inside the unit cell, and H1 just tells you what gives you the amplitudes from hopping from one unit cell to the nearest neighbor. So as you can see, with respect to the matrices H1 and H0, that's a linear system which you can solve. And perhaps the most surprising result that we discovered once we solved these equations, resolved these matrices, well, actually H1, it turns out you can parameterize it in this case by 2 angles. And what we discovered is that flatbands do not form isolated points. So despite being fine-tuned, they actually form continuous manifolds. So for any pair of angles, theta and phi, when it is colored squares, you can always find a Hamiltonian that has a flatband. The catch, of course, and this becomes apparent in the more complicated cases, is that these Hamiltonians might have a complicated hopping structure. As outlined here, and the physical lattices that we most likely happen to see in nature correspond to cuts of this flatband manifolds, and that's how they become they might become an isolated points. So things become less trivial in higher dimensions. This scheme works there as well. The problem is that now you have more choices, in principle more freedom. So you have to incorporate the lattice geometry, well, the Bravais lattice geometry, and then you have to extend it with the, then you have to make an assumption how you place the atoms in the unit cell, and this gives rise to further choices that you can make. But overall, the scheme works the same way. You first construct the compact localized state, and based on that, you reconstruct the Hamiltonian. At this point, I should also mention a complementary approach that was developed more or less in parallel. So far, I was dealing with the real space. You can also perform this construction in the Bloch space, basically following a very similar procedure. So you fix a lattice with a given special dimension number of bands. Again, you can pick a CLS, the compact localized state you want to have. In this case, you don't have any constraints on the amplitudes. You then can reconstruct the corresponding Bloch state, which is just a simple plane wave with the CLS amplitudes. And then by picking states orthogonal to this CLS Bloch wave, you can construct the Hamiltonian by basically considering operators that annihilate the CLS. By construction, this will give you a flatband in this case. And a simple example is the Lieb lattice, where we know the Hamiltonian, and Qi is this phase factor. So then the CLS amplitude is given by this expression, and the 2 orthogonal states that you can pick are given here, and then again, considering the bilinear combinations, you can construct various Hamiltonians on the Lieb lattice, which will all have a flatband in their spectrum. So this allows the algorithms that I described, the constructions, allow you to construct a single flatband in the spectrum for essentially arbitrary geometry, so long as you have finite range hopping and the system is translationally invariant. We also considered a much more fine-tuned case of all bands flat for the reason that it's a lot more sensitive to perturbations because all the bands are flat, and because it also corresponds to the complete localization, but simply due to fine-tuning. Evidently, a flat band implies zero group velocity, so in all band flat systems, if you place a particle, it never it remains confined in a finite region of the lattice. So now, an important result that we discovered here and that I will focus on from now is that despite these lattices being highly fine-tuned and thus seemingly hard to construct, there's a very simple generation principle that allows you to explore them all in one dimension and construct vast families in higher dimension. Essentially, they can all be constructed, let's say, one formulation of our result is that for such lattices in one dimension, their compact localized states are always orthonormal. That is, they provide a complete and orthonormal basis for individual flat bands, which also means that you can construct them simply by starting with decoupled sites, placing on-site energies assigning on-site energies to the sites on the same sublattice, and then simply applying local unitary transformations. This will guarantee you that the spectrum remains flat, and in 1D there's also proof that this explores the whole manifold of all band flat lattices. So there's all the lattices in 1D with all bands flat can be generated that way. In 2 and 3 dimensions, we do not have this generic proof. We're still working on that. We believe that this result still holds, but that is still in progress. And here is again the example for the 1D ladder. So you start with decoupled sites. You assign the on-site energies. You apply a local unitary that couples 2 sites in the unit cell. Then you can redefine the unit cell so that you now assume these 2 sites are in the same unit cell, and applying again a local unitary transformation, you end up with something that has a full set of hoppings, and yet by construction all the bands are flat. So let me give a brief summary of the construction part before I move on to the perturbations. So we found a way to systematically construct flat bands in real space, and there's also a way to do that in the Bloch space, depending on which representation is more convenient for you. It does rely in both cases on the compact localized states and applies to any space dimension lattice topology. Flat bands are not isolated. If you found one flat band Hamiltonian, you can always find a deformation that will keep it, although you're not guaranteed to have nice looking hoppings. They might get ugly. So now there are several extensions that are worth pursuing. One of them is non-Euclidean geometries, understanding, say, hyperbolic lattices, where people have already discovered examples of Hamiltonians with flat bands, typically based on Kagome lattice and other lattices for which the Euclidean counterparts have flat bands. Understanding what happens in case of no translation invariants, like DC field, quasi-crystals, or even disordered systems, which is possible. An interesting avenue is the driven systems, where in principle you can achieve flat bands without compact localized states, and then, yeah, thanks. And then try to understand how this change their reaction to perturbation. And finally, let me again mention the many-body Hamiltonians, where there are known examples of highly degenerate states in the many-body spectrum without any single particle counterpart. So understanding how to construct such systems and what kind of properties they have is also an interesting problem. So now I'll move on to the perturbations. So now that we have an idea how flat bands are constructed systematically, we can try and see if we can also understand in a systematic way what happens if we add perturbations. And the idea, of course, is that we explore, basically, we can explore various points in the flatband manifold we add the perturbation, and we ask how does it depend on our position on that manifold. So I'll focus on the all-band flat case where the systems are more sensitive, and the quick answer that I give is that different flat bands react differently, and as Carlo will demonstrate later, you can actually do further fine-tuning and get some interesting results in the many-body case. And the key let's say, technical tool that we are using is the basis of this CLS, which turns out to be extremely convenient in understanding the effect of the perturbation, while in case it is available. Okay, so let me briefly cover, in the remaining few minutes, cover the case of the disorder. So I'm interested in what happens if you take all-band flat system and you add disorder. So generically, the answer depends on the flatband type, the presence of the gap, and the disorder. So the previous studies have discovered a number of interesting phenomena, like unconventional scaling in 1D for very weak disorder, unconventional scaling of the localization length with vanishing disorder, even to the extent of finding constant localization length in the limit of vanishing disorder. Reentrant localization, where you start with localized state, you increase the disorder, the system delocalizes and then localizes again, or even critical states in case of the band touching. So using our all-band flat generator, what we did, we considered the manifold of all-band flat Hamiltonians for the simple case of the two-leg ladder. We added disorder and asked a question, what happens? So to understand that, we discovered that after adding the disorder, it's a good idea to apply, as you remember, the all-band flat Hamiltonian is constructed by starting with a decoupled network, applying the local unitaries. So now the idea is that we add the disorder and then we revert the local unitaries, which, for this construction, brings us back to the originally decoupled sites, which, of course, because of the perturbation, are no longer decoupled, but instead you get now an effective model, which turns out to be extremely convenient for understanding the localization properties. And what we found in the case of the infinitesimally weak disorder is that while in 1 and 2 dimensions in the simplest cases, so just on-site disorder, the system is always localized, although localization length might be enhanced. In 3D, you can actually achieve delocalization by exploring the flatband manifold. So there are flatbands where without the disorder, everything is localized. You add a tiny bit of disorder and the system immediately delocalizes. And yeah, sorry, if in case you're interested in further details, so Youngjun there has a poster with further details. We have also considered the case of the quasi-periodic potential in the 1D case, again with the idea being that in the absence of the flat bands, you observe a metal insulator transition. And we know that for all bands flat with the Aubry-Andrea potential, we should get an effective model. What we discovered is that there are no extended states in one dimension. However, one gets reach a structure of fractal states, including energy-dependent transitions from localized states to fractal. And again, I suggest to inquire Sang-Hoon Lee, who's there in the back, and here's a poster with further details should anyone be interested. And so with this, I conclude. So I presented very briefly a systematic construction of short-range translationally invariant flatbands in real space, and mentioned the Bloch space construction. I also outlined the systematic construction of all-band flat Hamiltonians and considered some of the perturbations, namely disorder, where we found reentrant transitions, delocalization, and fractal phases. And again, to advertise a bit, so Carlo will be talking about many-body interactions and how one can find nonergodic phases in that case. And kind of a very big, like a very simple statement is that what we find is that degeneracy plus weak perturbation typically leads you to an effective model where the degeneracy is lifted and the perturbation is no longer weak. And well, here I list the future directions, and I'm stopping here, and thank you for your attention.
Thanks, Alexei, for the nice talk. And we now have questions from audience. So we have question from Arul.
Yeah, thanks, Alexei. Just a basic clarification, your ABF is when all the bands are flat. That's coming from your construction of these
Yes.
local unitaries, as you're
Yes.
calling it. But if you take some typical Hamiltonian, you would have just one flat band. Is that
Well, I mean, if you by typical you mean
I
random,
mean,
it
typical
will.
where you have one at least? Yeah,
Yeah, typically, I mean, yes.
you would find one. And so when you say local again, it's still a single body. I mean, there's only a single particle dynamics, but by local you mean sites. It's local on the sites.
Yes, I mean
which
that.
is-
Well, I mean that. Well, essentially, this local unitaries. That means you have a sum of unitaries, which each of which acts just on a finite number
on a
of
finite
sites.
number. And can you then extend this to having fewer number of bands? I mean, flat bands from ABF to something where you have only
Oh yes,
one?
but I mean, you definitely can do that, and this has already been done. The problem is that, as I was saying, we believe that all band flats always have orthonormal set of CLS, and with this local unitary construction, this is always you always get that. While we definitely know examples of flat bands which do not have this property. So this way, let's say you cannot construct it with the local unitaries. What seemed to be the case is in 1D, if you start using non-unitary transformation, then this construction still works, but well, this is for now. I don't have any explanation to this fact. So you can use it, but only you can only then get a specific subclass of flatbands.
Thank you. Thanks.
Is there any other question? We have question from Zoom.
So I believe that from your construction, you will never get the non-zero churn number
Oh yes.
because you can always like smoothly connect it to the trivial band.
Yes. No, I mean, but well, we gave up on that because there's a theorem stating that you cannot have Chern number, flatband, and short-range hopping. So that's, I mean, if you want to achieve that, I guess the simplest way is to try the driven systems where you can get an effective Hamiltonian long-range hopping, or let's say no compact localized state.
I see. So you say that's some direction on the topological flat band. So that means you have the driven. I mean.
Yes, well, because otherwise, well, you can get winding number, but it's probably not so interesting. Yeah,
Okay.
so you need to go out of equilibrium to get non-trivial topology. I think that there's already a body of work where I think people they do not give examples. They try to understand if you assume you have such a band, what would be the properties and what are the constraints you might have.
Okay, thank you.
Is there any other question? We have question from the Zoom. So can you write the question? Yeah, we are seeing the question. Please write down the questions. Alexei, can you read the question?
Yeah. So, have you studied the dynamics of the CLS? Well, to the best of my understanding, I mean, it's kind of trivial because if you place a particle in a CLS, there will be just phase oscillations and that's it. It will just stay. I mean, it's an eigenstate. So the only So the dynamics is that of an eigenstate. The only difference is that it's compact.
Okay. So if you have no more question, then we should move to the next speaker. So thanks again, Alexei, for interesting talk.